In this video, we're going to look at inner product spaces. And we'll start with the definition. An inner product on a vector space V is an operation that assigns to every pair of vectors U and V in V a real number UV such that for all U, V, W in V and all scalars C that these are true. Again, I'm using the standard notation for the inner product, which is like commas. Again, another notation is the bar, but I'm going to use the comma here. And the definition, one of the first properties of the inner product is that UV is the same as VU. It'll give you the same values as long as you're dealing with real numbers. Right now, we're dealing with real numbers, so this is going to be true. Another thing that's going to be true is this. That if you have this, that can be broken down as this inner product, that U inner product V plus U inner product W. So notice the way it kind of breaks up. And 3 if you multiply a scalar times a vector, this first vector, it's the same as multiplying the whole inner product by that scalar. Then finally, if you take the inner product of a vector with itself, it's always going to be greater than or equal to 0. And 0 if and only if the vector itself is 0. And the vector space with an inner product is called an inner product space. That. So again, these are the properties of an inner product. You get UV is equal to VU. These break up this way. U inner product V plus W gives you UV plus UW. C times UV is the same as C UV. This is always positive when you take an inner product of a vector with itself, and it's zero if and only if the vector itself is zero. And again, a vector space with an inner product is called an inner product space. And one thing, just a note here, now notice up here that you have this property here. You can also kind of show that also say if you have U plus V W, that's going to be U W plus V W like that. Also, we have over here that if you take a scalar times one of the vectors, that's the same as taking the scalar times the dot product or the inner product, I should say. Also, you have U C V is equal to C U V, like that. Again, as long as we're working with real numbers, there's some other things if we have complex numbers. And also then, of course, from this, you can see some other things. Also, you have putting this together, what we had a minute ago, you can say that C UV is equal to C UV equal to UCV, like that. So that if you have CUV, that's going to be the same as UCV, like this. As long as we're working with real numbers. And again, you're familiar with one inner product already. That's the dot product. Dot product is a specific type of inner product. And so, and again, you remember the dot product was simply if you have UV, we have like two vectors. Let's say you have, it could be a two-dimensional or a three-dimensional vectors. put a bar over top. My hand keeps automatically doing it. So again, remember the inner product of the dot product is an inner product, which is U dot V, and that's going to be U that was the dot product, and that is a specific type of inner product. And we have another type of inner product. And let's make this definition. Inner product of functions the inner product of functions is defined this way. Let's say on an interval A to B. So the inner product functions on the interval AB is the number. Remember, the inner product always produces a number or a scalar. And so let's say if you have one function and another function, the inner product of those two functions is defined this way. Once again, you put in two vectors, so to speak. Now, in this case, the vectors are going to be functions. Where F1 and F2 are functions. On that interval. And now what we're going to try to do is show that this is an inner product. So let's start with each of our definitions. Let's start with the first one. Remember, our first definition said that we had to show that you could basically commute those two. So we said before that you could commute those two. And again, now here, I'm probably being a little bit sloppy with notation. Here, before I called the inner product the angle braces, here I have just the round braces. Let me fix that. So let me write it that way. But in case, let us show that the first property applies. So if we do AB, F1, X, F2, X, dx, so just write it down in the normal definition. And now, of course, because these are just two real valued functions, we can commute those. So we're allowed to do that. Now, what do we have here? If we would reverse the process, that's going to be the inner product of F2, F1. So we showed our first property that F1, F2 is equal to F2, F1, and we did that by just using the definition of our inner product, commuting those, which we're just using real valued functions to show that they can commute. And then we have this equal to that. The other thing we want to show is number 2, that you can take a constant times one of the functions and then factor it out. So let's do that. So C F1 F2, again, that's going to be equal to the integral a to b C F1. I'm going to leave off the notation, the x, just to make it a little bit simpler. F2 dx. And now by the property of the integral, remember, if you have a constant, you can always factor that out of the integral. And so, and of course, this is the definition of our inner product. We have this. So we showed that the constant times one of our vectors, so to speak, with F2 is equal to that constant times that inner product. Another property we want to show, I guess I'm doing these a little bit out of order. We want to show start with let's start with F1, and let's say we have an F2 plus F3. And let's work with this right here. And so now remember what we're trying to show with this one. We're trying to show if we have this vector inner product with these two vectors, we can break those up. So let's do that. So all I'm doing is just multiplying these through. Like this. And now by the definition of an integral, we're allowed to write this as F1, F2 dx. F1, F3 dx. So just by the properties of an integral, you're allowed to always say that the integral of a sum is equal to the sum of the integrals. And so now what does that leave us with? That gives us F1, F2, F1, F3. Which is what we wanted to show. We wanted to show that if you have an inner product of a vector with the sum of two vectors, that's going to be equal to inner product of this first vector with the second one plus the first vector with the third one. That's exactly what we had here. We started with this, and so we have F1, F2, and F1, F3. Finally, we want to show that this inner product is always going to be positive or zero if you have a vector with itself. So it's going to be F1, F1 dx. F1 squared dx. And of course, you know what we're doing here? We're integrating over something that's always going to be positive. You can imagine whatever our function is, it's going to be, it has to be positive because we're squaring the function. And in its most basic form, the integral is the area under the curve. So if this is always positive, this area always has to be positive. So that's always going to be greater than or equal to 0. And it can only be 0, as you can see, if the function itself is 0, because if it has any, even just one place where it's above 0, you're going to get some kind of positive area. Okay, so we proved that this defines an inner product. And this is a very important inner product that's used many, many times in other places. Now, closely related to the inner product is the length of the norm. We'll start with the definition. Let U and B be vectors in an inner product space. Length or norm of V is defined this way. So in other words, if you want the length or norm of a vector V, it's defined precisely this way. The length is going to be the square root of the inner product of the vector with itself. And another thing that we need is the distance. The distance is defined this way between two vectors u and v. And 3 u and v are orthogonal if u inner product v is 0. So again, this is the definition of a norm. And then there's a more precise definition of a norm you can also go by. Let me put this definition. So here's the more precise definition of a norm. A norm is such that it's always going to be positive or zero, and it's going to be zero if and only if the vector itself is zero. You can factor out a scalar out of a norm as long as you use the absolute value. And what's called the triangle inequality is that u plus v is less than or equal to u plus v. Again, this is the triangle inequality. So that's the most precise definition of a norm. And another very important theorem is called the Cauchy-Schwarz inequality, which says if you take the absolute value of an inner product that's less than or equal to the product of the norms of each of those two vectors. And this is equal only if u and v are scalar multiples. And we already saw the triangle inequality, which is another very important inequality. And this is something that's going to come up time and again. There's a theorem that says an orthogonal set of non-zero vectors is linearly independent. So if you have a set of vectors and they're all mutually orthogonal, then they're going to be linearly independent. And the most obvious, we can pick up, let's just pick an example here. Let's say if you have 1, 0, 0, and let's say you have let me just use sort of the standard -3, 0, 0, 0, 14. And let's say our inner product is the dot product. Then if you do the dot product with all of them, all the pairs, you get 0. Zero, 0. So we've taken all the dot products between all the pairs. We always got 0. So they're all orthogonal. Therefore, they are linearly independent. So again, this is a very important theorem here that we're going to use many, many times. An orthogonal set of non-zero vectors is linearly independent. So let's do some examples here. Are the functions Are these functions orthogonal on the interval 0 to 2? So let's take a look at that. Remember, they're orthogonal if their inner product is 0. And again, since we're dealing with functions, again, let me just write sort of a simplified notation here. This is going to be f1, f2, dx from 0 to 2. And put our functions in e to the x, x e to the minus x, e minus x, dx. Now, when we multiply these two together, we're going to have e to the x times e to the minus x. So we add the exponents, we'll end up getting e to the 0 minus e to the 0 over here as well. And so that's going to be 0 to 2x minus 1 dx. Integrate that. And so it's going to be 4 divided by 2, which is 2 minus 2, which is 0. So we got the inner product of those two are 0. Therefore, f1, f2 are orthogonal. So let's consider these functions on -2 to 2, and where we have constants, where C1, C2 are constants. Now find C1, C2 such that F1, F2, F3 form an orthogonal set. And so let's take a look at this. So first of all, let's just check to be sure F1 and F2 are orthogonal. So let's check that. If we integrate this, so this is going to be 2 to the 4th minus 2 to the 4th, so that'll become positive. So that's 0. So those two are orthogonal. Now we want to be sure that this and this is orthogonal, and this is orthogonal. Let's start with the pair F1, F3. And so we're going to multiply these out. So I'm going to skip some stuff. So I'm going to take F1 times F3, and that's going to give us x squared plus C1x cubed plus C2x to the fourth dx. And then let's integrate this. And of course, if we integrate, we won't have this. And let's put these values in. So I'm going to take some shortcuts here. I'm going to put the values in here and then put this in here. And then certain things are going to cancel out. So when we do all this, just to save some time, we end up with 16/3 plus 64/5. And what happens is we end up having over for this value here, we're going to end up 2 to the 4th over 4. And then we put this one here on the lower bound, we end up with minus negative 2 to the 4th over 4. So those two are going to cancel. And then we're just going to be left with 4 terms total. And we add these ones with a third in it, we end up 16/3 and 64/5. Set that equal to 0. And then we end up with 64/5 C2 equals negative 16/3. C2 is negative 5/12. So we need, for these two to be orthogonal, we need C2 to be negative 5/12. And so finally, let's check the last pair over here. F2, F3. Once again, I'm just going to put them in directly. So I'm going to just multiply this, this times this. So we're going to end up getting negative 2 x cubed C1x to the fourth and again, go ahead and integrate this. That's going to be from negative 2 to 2. And once again, when we put these bounds in, notice these even bounds, these even x's are going to end up canceling out again because we'll have 2 to the 4th, and then we have minus 2 to the 4th, 2 to the 6th, minus 2 to the 6th. So those are going to cancel. So we're really going to only end up with this. And so like we'll end up with C1 2 to the 5th divided by 5 minus C1 negative 2 to the 5th divided by 5. And then these will all end up being 64 fifths C. Well, once again, we want this all to come out to 0, so we set this equal to 0. And of course, this time 64 fifths C1 is 0. This will end up being 0. So again, we wanted the inner product to come out to 0. And we got that value. And before we got C2 is this. So let's put those all together. So that means F3 is going to be x plus 0, x squared, plus minus 5/12. X cubed. And that's going to end up being, I guess, yeah, just that. So F3, if we make F3 equal to x minus 5/12 C3, in other words, we just made this 0 and this negative 5/12, we end up with this. Then the whole set. So if C1 is 0, C2 was negative 5/12, then F1, F2, F3 form an orthogonal set. And therefore, they would be linearly independent, just to throw that in. Norm of f squared, which is equal to the norm of the sine squared. And remember, by definition, the norm is the square root of the inner product of the function with itself. And what this whole thing squared. And then this is going to be the square root from 0 to pi over 2 of sine x dx. And again, this is just squared. Sine squared x 0 to pi over 2 dx squared. We could have actually gotten rid of that square root a while ago. So we actually want the integral of this. So let's go through this. And so, of course, remember, anytime you want to integrate sine squared, we use the half angle relations. And integrate this little 1/2 sine 2x divided by 2, 0 to pi over 2. That's going to be 1/2 2 half sine 2 pi over 2 over 2. minus the lower bound, which could be 0 minus 0. And this is actually going to be 0 here because that's going to end up being sine of pi. So we're going to have 1/2 pi over 2, which is pi over 4. So that's the norm of f squared.